I feel extremely happy to meet the viewers of my channel in yet another video, that is Control Systems Lecture Series Lecture 24, State Space Analysis. I hope the viewers would have enjoyed my previous 49 videos in this channel. I am sure the viewers will enjoy this video also. I request my viewers to share this video with the learning community so that the learning community gets benefited to a greater extent. I also want the viewers to subscribe my channel. Further, I want my viewers to post the queries or comments or feedback in the chat window available in the YouTube channel, or even you can send it to me by email or WhatsApp. So I am sure you will render your support as you have done so far. Thank you. Let me move to the video straight away. In this presentation, we are going to emphasize the importance of state space representation and to obtain the state space representation of electrical systems. So these two are the primary learning objectives of this particular video. So we are going to see how to represent the state model for a given electrical system. Before that, what are the advantages of state space model over the classical transfer function model or classical control model? We are also going to introduce the concept of state variables, state equation and output equation. In classical control or the transfer function based control, the modeling was done only using the transfer function approach. That means we have written the equations in time domain by applying the appropriate physical laws. Then we have taken the Laplace transformation of the equations with the assumption of zero initial conditions. Then we have carried out the design and analysis of the classical control based systems with variety of graphical tools. So we have seen in our previous videos the root locus plots, Bode plots, polar plots, Nyquist plots, Nicol chart, etc. So the graphical tools were extensively used for analyzing the transfer function approach. So no doubt the classical control is simple, attractive and powerful. However, the classical control has got some drawbacks or limitations. Number one, the classical control is applicable only to time invariant systems, linear time invariant systems. But in real time, the systems are non-linear and time variant too. And this particular classical control is restricted or constrained to the analysis of scissor systems only, single input, single output systems only. But in real time, when we go for process control applications, we may have to use number of inputs and we have to analyze the internal variables, intermediate variables, and we may have to control a lot of output variables and intermediate output variables. So the systems are not simply scissor systems. So they are MIMO systems. Right. Then another limitation is it gives the output for the given input. That is a black box arrangement. For the given input, what is the output? It does not actually give the information regarding the internal structure or internal behavior of the system. And since we take the initial conditions as 0, it is applicable only for 0 initial conditions. And when we take the state variable analysis, which we are going to introduce here, they are applicable for systems with non-zero initial conditions also. That means even if the initial conditions are present, we are going to consider them. And these state variable analysis is not only applicable for linear time invariant systems, applicable for linear, non-linear, time variant, time invariant, MIMO, SYSTO. Any type of system it is applicable. And we get the information regarding the internal states or internal structure of the system. So that is why we go for state variable analysis. Now we will see what is state variables. Generally, state variables describe the dynamic behavior of the system, like how we describe the different variables in a system. We have state variables, but these state variables are called internal variables, the variables present in the system. What is this internal variables? We will see. So state of a system is represented by minimal set of variables called state variables. Therefore, when I want to represent the state means in a literal meaning, English meaning, state means status. Status of a system is represented by minimal set of variables, only minimum number of variables. Those variables are called state variables, whose knowledge at t equal to t naught, that is initial time, normal initial time is 0. So the value of the state variables initially along with the inputs applied from t greater than or equal to t naught, because we normally apply the input only when t is greater than or equal to t naught. That is, the moment that we apply the inputs we call t naught or 0 time. So we need to know the knowledge of inputs and applied from t equal to t naught, then state variables at t equal to t naught, and with these two we can represent the dynamic behavior of the system for any time greater than or equal to t naught. That is, from the moment the system is switched on till the system is switched off, what is happening exactly inside the system, we are going to analyze with the help of the state variables. That is the meaning. How to take the state variables? State variables are nothing but the variables which are associated with the energy storing elements. What are the energy storing elements in an electrical system? We know very well that inductance and capacitance. So inductance and capacitance are going to contribute to the state variables. Resistance is an energy dissipating element. And always the number of state variables is same as the number of energy storing elements. So you see, you count how many energy storing elements are present in a system, that much state variable you have to take. Otherwise, if the order of a system is nth order system means n state variables we have to choose. That means always we will have order of the system as same as the number of energy storing elements. That's all. Now we will understand how to choose state variables and how to obtain state representation. For example, we have a control system. We have an input and we have an output. Normal control system, only one input, one output. But in state space approach, we also take one more called state. So this is input, this is state, this is output. So describing the relation between output and input and state, that is output expressed in terms of input and state. Similarly, the derivative of the state variable expressed in terms of state and input is actually called state space representation. We will see how with the help of an example. It is not necessary that we may have to have only one input. We can have any number of inputs. That is why m inputs are shown in the next block. So u1, u2, etc. um. Similarly, any number of outputs are possible in a system, y1, y2, etc. yp. And n state variables, because order of the system is decided by the number of state variables or number of energy storing elements. So x1, x2, etc. xn. Therefore, in a control system with m inputs, p outputs and n state variables, we should analyze how to obtain the state space representation, or in simple term, I should relate x dot, that is x1 dot, x2 dot, xn dot in terms of input and x1, x2, xn. Similarly, output y or y1, y2, etc. yp in terms of state and input. That is what we call state model. That's all. So these m's input variables u1, u2, etc. um is also called input vector. P output variables y1, y2, etc. yp output vector, n state variables x1, x2, etc. xn are called state vector. So that representation is called the state vector. Right. So in a state space analysis of an electrical system using physical variables, we have already seen inductor and capacitor are the energy storage elements in electric circuit with RLC. So here, whenever we say inductor, rate of change of current is going to be the variable L di by dt. L di by dt. Similarly, rate of change of voltage across the capacitor is the variable as far as capacitance is concerned, because inductor always opposes change in current, capacitor always opposes change in voltage. This we know very well from the fundamentals of circuit theory. Therefore, these two things are considered in modeling and hence state space representation. Therefore, this current through an inductor and voltage across capacitor are selected as state variables, that's all. So input variable is nothing but your electrical sources, voltage source, current source, all that. Output variable may be current or voltage in an energy dissipating element. So state variable or state variables mean current or voltage in energy storing elements. That's all. Therefore, how to obtain the state space analysis? Choose first of all the state variables, that is, first you find out the elements corresponding to the state variables. So inductor, capacitor, all that. Then you take the inductor current, capacitor voltages as the state variables. Then express the relation between the state variable and derivatives. That is what I have said in the previous slide also. X dot, that is x1 dot, x2 dot, xn dot, try to relate in terms of state variable, that is derivative in terms of state variables and input. For this you apply Kirchhoff's laws, then rewrite the equations in a proper form, structured form, formulate the state model. That means I should write the equations for derivatives of states, then output, that's all. In both the cases, the right hand side will be in terms of, that is, combination of inputs and output. As far as state equations are concerned, output will not come. But in the case of output equation, it is output in terms of state and input. So in derivative of state, we will get x dot in terms of input and state. Again, output in terms of input and state. Let us see how to do it. So this is an example. So it's a two loop electrical circuit. So here you can find, we have to obtain the state model. So there are two inductors and one capacitance. That means 1, 2, 3, these three elements are going to contribute to the state variables. So inductance means what should be chosen? Inductor current. So this inductor current, this capacitor voltage should be chosen as the state variables. That's all. That is what we have done. I1, I2, Vc are chosen as state variables. What are the input variables? E1 voltage source E1, here E2 voltage source E2. Therefore, we will see how to do it as per the steps already put in the previous slide. So first we have to do the circuit equation modeling, right? So we have to apply proper laws. So we can apply KVL as an illustration. So here what I have done is branch currents are assumed. Here one branch current, here one branch current, here one branch current. So that is why this is plus, this is minus, this is plus, this is minus. Where the current enters plus, leaving minus. Similarly here this is plus, this is minus, this is plus, this is minus, this is plus, this is minus. However, for the purpose of writing the equations, loop currents are used. So I1 in clockwise direction, I2 in clockwise direction. So if we apply KVL to the loop 1, that is this loop, so here minus to plus E1 of t. So here the branch current direction is this direction, we are going against. Therefore it is a rise. So plus I1 R1. So here again branch current is like this, we are going like this. So plus L1 dI1 by dt, because L dI by dt is the voltage across the inductors, we know very well. Then when you go from here A to this, so plus to minus voltage across the capacitor, so minus Vc, so here nothing, so equal to 0. So that is first equation. Second equation, apply KVL to this loop. So apply KVL to this loop. So if you see, So here minus I2 R2. We are going in this direction. In our direction, this plus minus comes. Therefore, minus I2 R2. Then here, like this only we are going clockwise. So minus L2 dI2 by dt. That is how we have written like this. Then here plus 2 minus minus E2. So here minus 2 plus Vc. Here when we travel in the first loop, we have traveled from top to bottom, that is why minus Vc. Here we have gone from minus to plus in second loop, that is why plus Vc. These things we know very well from the fundas of circuit theory. So rearranging this, Vc equal to I2 R2 plus L2 dI2 by dt plus E2 of t equal. That is second equation. Then if we apply KCL at this node, because this is one current, this is another current, this is another current. So apply KCL at this junction. So this is current leaving, this is again current leaving, this is again current leaving. So sum of currents leaving is 0. So this is your I1 and this is your I2. So I1 plus I2 plus, so this is C dVc by dt equal to 0. So don't get carried away by the plus sign, minus sign and all. We can do in any way. So I1 plus I2 plus C dVc by dt equal to 0. So this is one current I1, this is I2 and this is C dVc by dt. Or we can take this is I1, right? This is I2, this is C dVc, right? So summation is 0. Now the input variables are nothing but the voltage sources E1 of t, E2 of t. So that is given some notation U1, U2. So U1, U2 means input. State variables are represented by the notation X1, X2, X3. What are the state variables? I1, I2, then Vc. So I1 is taken as X1, I2 is taken as X2, Vc is taken as X3. That's also state variables be current, voltage in inductance and capacitance respectively. So L1, L2 and C. That's also here it is not only L1, L1, L2. So here we get L2 also. So L1, L2 and C. So if we substitute these state variables and input variables, that is instead of this I1, I2, Vc, E1, E2, if you substitute the state variables and inputs, how these equations 1, 2, 3 get transformed, we will see. Let us see how this equation we got. What is E1 of t? E1 is U1, that is what we have written U1. What is the next term? I1 R1. What is I1 X1? Therefore R1 X1. That's all, X1 R1. What about the next one? L1 di1 by dt. What is di1 by dt? X1 dot. That is dx1 by dt or x1 dot. So L1 x1 dot. Next. Minus Vc. What is Vc? X3. So minus x3. Minus x3 equal to 0. Here we have to write as derivative of state vector. So x1 dot, derivative of a state variable. So from this if you write x1 dot, how to write x1 dot? Divide everything by L1. 1, 2, 3, these terms you bring it to the right hand side. Divide by L1, you will get this equation here. So I1 is x1, that is dI1 by dt is x1 dot. So x1 dot is this. So this is equation here. Similarly, from equation to L2 di2 by dt, that means that is Vc means x3, R2 x2. Why R2 x2? Because I2 is x2, so L2 di2 by dt. So L2 into x2 dot plus what is E2 of t? U2. That is what we have written. Yeah, that's all. Similarly, you write x2 dot from this. In the same way how we have written this x1 dot. So write x2 dot. So we know I2 equal to x2. So di2 by dt is x2 dot. That is what we have done here. Right. Similarly, the next equation, third equation, I1 plus I2 plus C dVc by dt. What is I1? X1. What is I2? X2. What is dVc by dt? Dx3 by dt, that is x3 dot. So x1 dot plus x2 dot plus C x3 dot is 0. That is what we have written here exactly. So from this you write x3 dot. Therefore what we have done is we have taken Vc as x3, that is dVc by dt is x3 dot. For that only we have written equation. So equations A, B, C, that means these three equations are called state equations. So how many state equations are there? Three state equations are there. How many state variables are there? Three state variables are there. Therefore, three energy storing elements, three state variables, so three state equations. So you can see in all the three state equations, derivative of the state variable expressed in terms of states and input. So x1 dot is expressed in terms of x1, x3 and u1, states and input. x2 dot expressed in terms of x2, x3 and u2, states and input. x3 dot is expressed in terms of states. Here input doesn't come because of the nature of the equation. And this we can write in general form as x dot equal to ax plus bu in a vector matrix notation form. So x1 dot, x2 dot, x3 dot, it is written as a vector. So it is called the derivative of state vector. And x1, x2, x3 state vector, u1, u2 input vector. Now the coefficients of x1, x2, x3, u1. What is the coefficient of x1? Minus r1 by l1, that's all. Coefficient of x2, 0. Coefficient of x3, 1 by l1, we have written. Coefficient of u1, minus 1 by l1. Coefficient of u2 is nothing, so 0. Right. Similarly, x2 dot. So here x1 coefficient is not there, 0. x2 coefficient is minus r2 by l2. x3 coefficient is 1 by l2. Third equation, x1 coefficient is minus 1 by c. x2 coefficient is minus 1 by c, and x3 coefficient is not there, no input terms. Here you have input term corresponding to u2, so minus 1 by l2. u1 coefficient is not there. So I hope you have understood how to write this vector matrix notation form of state equations from the state equations that we have established A, B, C from equations 1, 2 and 3. So equations 1, 2, 3 are nothing but the modeling of the system. So from the modeling we choose state variables, and then from the state variables we write the derivatives of each state in terms of states and inputs. That's all. Similarly we have to write output equation. Output is Cx plus du form we are going to write. What is output? We are going to take outputs as voltage across resistance R1 and R2. It is not necessary that we have to take only like that. We can take in any way. Here we are going to take the voltage across the resistance, that is this and this are taken as the outputs. So if we take them as outputs, so y1 is I1 R1 because current flowing through R1 is I1, so I1 R1. Current flowing through R2 is I2, so I2 R2 is the voltage across R2. We know I1 is x1, I2 is x2, we know very well. That is how we have chosen. Therefore, y1 is x1 R1, y2 x2 R2. Like how we have written ABC from equations 1, 2, 3, we are going to write, that's all. So, y1 is x1 R1, y2 is x2 R2. Therefore, if we write these two equations in the form of matrix, vector matrix notation, y1, y2, column vector, output vector. So, x1 coefficient is R1, there is no x2 coefficient 0, x3 coefficient is also not there 0. In y2, x1 coefficient is not there, x2 coefficient is R2, x3 coefficient is 0. There are no input terms, therefore plus du will not come. Therefore, we can easily obtain the state equations and output equations. The state equations and output equations put together called state model. Therefore, in any state space representation, obtaining the state model is very, very important. So, writing the state equations and writing the output equations. So, this is y is equal to cx. Therefore, this c is this. Therefore, d is 0 here. Ax plus bu, this a is this, b is this. Now, we will generalize this for any system. That is what we are going to do in the next slide. So, state model, state equations. So, general form of state equations is x dot equal to ax plus bu. That is what we have seen. X dot equal to ax plus bu. Right. So, here there are n states. In this case, we have taken only 3 states and 2 inputs. In general, you can have n states. Therefore, a11x1 plus a12x2, etc. a1 one xn. That is, whatever we have written, no, the coefficient of x1, x2, x3, so all these coefficients are written by the respective subscripts a11, a12, etc. a1n. Similarly, the input coefficients, no, so input coefficients, these coefficients are generalized as b11, b12, etc. b1n. Similarly, we do for all the n-state equations. Therefore, this matrix A, which is a 3 by 3 matrix, will become an n by n matrix. So, first row is a11, a12, etc. a1n. Second row a21, a22, etc. a2n. Last row is an1, an2, etc. an. Therefore, this is nothing but a n by n matrix called system matrix. This is going to represent the behavior of the system. This is a system matrix A. This x1 dot, x2 dot, etc. xn dot is derivative of state vector. x1, x2, etc. xn is state vector. What is the order of this? N by 1. If you see in this example, we have 3 by 1 order derivative of state vector. Then this is 3 by 1 order state vector, and this is 3 by 3 order system matrix, and this is input vector 2 by 1 order vector, and this is the coefficient matrix B, so B 3 by 2. So if we generalize Bn1, Bn2, etc. B1m, similarly B21, B22, etc. B2m, Bn1, Bn2, etc. Bnm. That means here you can see three rows. Why 3 rows? 3 states. Why 2 columns? 2 inputs. So it is a 3 by 2. What is that 3 representing? So 3 represents number of state variables. What is the 2? 2 is nothing but your inputs, number of inputs. So 3 by 2, therefore for a general system, n state variables, m inputs. So n by m, that's all. So B is an input matrix of order n by m. I hope I have clarified how to write this n by m, n by n, n by 1 state vector. This is m by 1. Because there it was 2 by 1, 2 inputs. Any number of inputs m, so m by 1. Similarly, we will see the output equations. So there are p outputs. So again we have written the outputs in terms of states and inputs. So for your understanding, here I have taken only 2 outputs. This is 3 by 1 order state vector. Here 2 rows, 3 columns. Why 2 rows? 2 outputs. Why 3 columns? 3 states. So 2 by 3, 2 represents number of outputs, 3 represents number of state variables. Therefore, in this P outputs, therefore P rows, how many, P outputs, so P rows, how many columns? N columns, because N state variables. So P by N. So there we had 2 by 3. So here we have P by N as a generalization. Anyway, there we did not have any coefficients for U, but here we are writing. We can have this U1, U2, etc. UM, because M by 1 vector, this is M by 1. Therefore, what should be order of this? Very simple. See, this is P by N. This is n by 1. P by n by 1 is what? P by 1. Therefore, here we should have P by m, then only P by m by 1 by matrix multiplication. It will convolve to P by 1, that's all. Therefore, C is this output matrix of order P by n. D is the transmission matrix of order P by m. Now, how to represent this, output equations and the state equations in block diagram form. X dot equal to ax plus bu. Y is cx plus du. That's all in simple form. X dot is ax plus bu. This entire thing is x dot is equal to ax plus bu. This entire thing is y is equal to cx plus du. X dot we want. Therefore, we have to have state variable x of t. That means x multiplied by the matrix A. Therefore, we have to have a block with the gain A. So, A is nothing but that matrix A. What matrix A? This matrix A. What is B? This matrix B. That's all. So, B should be multiplied by U. So, x dot is Ax plus Bu. So, U into B, A into X, they are added in a summing point. What do we get? X dot. But we have to get X. What to do? We have to put N integrators. So, here it is not one integrator, N integrator. So, X is integration of X dot of T, X of T. That's all. How to get output equation? Cx plus du. Cx plus du. Therefore, feed this x of t to a block with the gain c. C is nothing but your in this matrix, output matrix, right? Then d into u. So u into d means we should have a block with this matrix d. So these two have to be added. Cx plus du. Addition will give you y of t. The same thing can be represented by a signal flow graph. So this B is a branch with the gain B, and this addition a node x dot, and this is integrator, and this signal is represented like this. Even we can put 1 by s here, x of t, C, this C gain, I mean this gain and branch, and this is the addition of these two. Therefore, here we put another node. So u of t into d. So u of t feed a signal with the gain d, that is matrix d. We will get out. Very simple. So x dot equal to ax plus bu, y is equal to cx plus du. If you arrange in proper form and then block diagram and representation and signal flow graph representation, if you do, then that is your state model. So in this next video, we will see how to represent the state space representation for a mechanical system. So till then, goodbye and thank you.